Hello everyone, I am Mr. Ish. Let's get back into these integral template videos. We'll be looking at integrals of exponential, natural log, and power functions. You have to learn the templates of these. Anything which looks like e to the ax in terms of its integrand, when you integrate it, the antiderivative for an indefinite integral would look like e ax over a plus c. So you have to remember this template. Likewise, anything which looks like natural log x dx, when you integrate it, you're going to get x natural log x minus x plus c. Lastly, a power function which looks something like this, when you integrate it, you're going to get b to the x over ln b plus c. In each of these instances, these antiderivatives, you can take the derivative as a good exercise for yourself and take it back to these original functions. So let's look at this first question. We're doing a definite integration of e to the minus x. You know the template over here for something which says e ax. When you're doing the integration, you're getting e ax over a. Here, a is equal to minus 1. So when you do this, it's not hard. You're going to get e to the minus x divided by minus 1 by means of this template. You're going to get minus e to the minus x, but you know you can't forget these intervals infinity and 0. You have to do just definite integration here. You'll have minus e to the minus infinity minus e to the 0. Minus 0, 0, it doesn't matter. This right here is the same thing as 1 over e to the infinity, which is literally 1 over infinity minus 1. And this zeroes out. You have minus times minus 1, you'll get 1. And that right here will be your answer, and it would be right. This next question is not hard. You could literally push 2 outside and look at everything like this. ln x dx, we know the template for natural log x. I've shown it to you. You're going to have x ln x minus x. That's your antiderivative coming out from this. E upper limit and 1 lower limit. The hardest part in this question is not this antiderivative, but how you place these, and I'll show you how you do it. You'll put the e's first, then you put the 1s in place of x's, and you'll compute. You'll have e ln e minus e. This is with the result of e feeding in. Then you have the minus from the difference aspect of upper and lower limit. Then you have 1 ln 1 minus 1. This ln 1 is a 0, it zeroes out. Here you'll get e minus e. All of this will zero out. And here you'll have just a minus 1 remaining. This zeroes out because e minus e is a 0. You have a 1 times 2, and your final answer is a 2 for this definite integration, and you're done. Not hard. This right here is a power function. Looks something like this. An integration of bx dx. You know it's b to the x over ln b. B here is represented by 2. When you do the antiderivative of this, you're doing 2 to the x divided by ln 2. You're doing from an upper limit 4, lower limit 3. You're doing 2 to the 4 minus 2 to the 3. This is your definite integration part divided by ln 2. Your final answer can be 16 minus 8, which is 8 divided by ln 2. And you can compute this as a decimal, or you can leave it as is, and it would be good. Now in this question over here, we are looking at an integral of an exponential, but there's some busyness over here. So you know we have to use polynomial substitution. If u is equal to minus t cubed, du is equal to the derivative of this minus 3t squared dt, and dt is equal to minus du over 3t squared. It's indefinite. We'll have a function as our final answer, and then we just have to compute this through. We have t squared, then we have e to the u, and we have du. We have a minus from out here. I can bring this 1 over 3, this 3 coming out as a 1 over 3, this minus coming out. Here remaining on the bottom I have a t square. The t squares cancel out. This right here is just basic polynomial substitution, but we're looking at different functions now. We have a minus 1 over 3, integral of e to the u du. Integral of e to the u is just e to the u. You have a minus 1 over 3 sitting out, and you have to resubstitute back. You'll have a minus 1 over 3 e to the u, and u was this minus t cubed plus c. If you want to be a little more fancy, you can get rid of this negative exponent. We'll have a minus 1 over 3 e t cubed plus c, and you would be right with that answer. Another polynomial substitution. Remember, don't let the word polynomial substitution confuse you. In the end, polynomial substitution can be used for any kind of functions. Here you can say u is equal to sine x, and then du is equal to cosine x dx, and dx is equal to du over cosine x. You have to do this substitution. Cosine x, b to the u, and then du over cosine x. These cancel out. You're just looking at of this type. Integral of b to the u, du will be, like I showed you based on the template, it will be bu over ln b. You can resubstitute the u, it will be b to the sine x over ln b plus c, and this right here is your final answer, and it's right. Initially this question might look hard, but it isn't. You'll do again polynomial substitution, and this right here is a composite, so you focus on that. U is equal to x cubed, du is equal to 3x squared dx, and dx is equal to du over 3x squared. This coefficient can be pushed out, so let's do that. We have an x squared ln u, and then we have a du over x squared, but we have a really 3 sitting here in the denominator. We can push it out as well. These x squares cancel out. We have 4 over 3 ln u du. In terms of the antiderivative of this is the most complex. You'll have 4 over 3 u ln u minus u plus c. You have to substitute all of these u's, and you'll have x cubed ln x cubed minus x cubed plus c. And this right here is your final answer. The antiderivative for ln x integral is complicated, but we'll show you how you derive this using integrating by parts technique when we talk about it. So that awaits us. The integrating by parts technique is a specialized integration technique we'll talk about in a future video, and we'll look at how we can derive this to be x ln x minus x plus c as the template for this natural log x. Anyhow, let's focus here on the question. U is equal to e to the x, the composite. Du is equal to e to the x dx, and dx is equal to du over e to the x. In all of these instances, you have some sort of function and an antiderivative, so you can always get away with the polynomial substitution technique. So you have e to the x ln u du over e to the x. Again, these things cancel out, and you'll just have ln u du. So from here it's no different than just going and following this template over here, which is what we'll do. We'll resubstitute after we've created the template here, u ln u minus u plus c. We have to resubstitute the u's, which are e to the x ln e to the x minus e to the x plus c, and this right here is my final answer, and that's good. This here serves as our last question. Always use polynomial substitution where and when possible, especially when you have composites involved. Here's my item which will be substituted. If u is equal to ln x du is equal to 1 over x dx, the derivative of ln x dx is equal to x du. Let's come over here, bring this 2 out. We have a 2, we have a 1 over x, this 1 over x. We have b to the u, and then we have x du, which is right over here. I'm bringing it right here. This x and this x cancel out. We essentially have 2 integral b to the u du. You know, the template scheme for this is easy. We're going to have 2b to the u over ln b plus c. We just have to resubstitute the u. We'll have 2b to the ln x divided by ln b plus c, and this right here would be our final antiderivative function, and it would be right. So our video, which is relatively short and easy, ends with this. Anytime you have something which looks like this, e to the ax, in terms of an integrand, the antiderivative is just e to the ax over a plus c. Anytime you see natural log x dx, it's x ln x minus x plus c. Rather convoluted but easy to derive using integrating by parts technique. Likewise, b to the x dx is easy. It's b to the x over ln b plus c. In all these instances, you can easily do the derivatives back and end up right over here for each of these antiderivatives, and it's a good exercise to do that. And that's it for this video. Not too hard, easy, simple, to the point. Thank you for watching. Have a nice day.